All right, welcome. Today, we're going to pull back the curtain on something we all rely on but maybe don't think about too much: credit card fraud detection. We're going to break down how these digital guardians are built, literally from the ground up, from a single piece of data to a fully working system. So, let's dive right in.
Think about it. You're just, buying your morning coffee, and ping, you get a text from your bank. Hey, did you just try to spend $500 on a flight to another country? How on earth does that happen in milliseconds? Is it some kind of magic? Or is it something a lot cooler?
Yeah, spoiler alert, it's not magic. It's a really carefully designed system. And this mind map right here, that's our blueprint for today. It lays out the entire life cycle, from grabbing that first bit of raw data all the way to deploying a digital guardian that keeps your account safe. Okay, so every great detective story starts with gathering clues, right? Well, in our world, those clues are data. This first phase is all about collecting the raw evidence, and then, just as importantly, cleaning it all up so our digital detective can actually make sense of it.
So what kind of clues are we talking about? Well, every single time you swipe, tap, or click, you generate a whole data set. This includes the basics, a unique ID for the transaction, the dollar amount, the exact time, who the merchant was, and the location. And here's the most important part for building our system. We need a label. For transactions in the past, was it fraud or not? This is the raw material for absolutely everything that comes next. Now, you might be thinking, great, just toss all that data into a computer and we're done. Well, not so fast. Raw, real-world data is notoriously messy. I mean, it's often incomplete, it has errors, duplicate entries. Feeding that mess directly to our model would be like trying to solve a jigsaw puzzle with half the pieces missing and a few from a completely different box. It's just not going to work.
And that's where the cleanup crew comes in. This is data pre-processing. First, we deal with any missing values and get rid of duplicates. Then comes this really cool part called feature engineering, where we actually create new, smarter clues from the data we already have. For instance, we could create a feature like the average transaction amount for this user to help the model spot when something is way out of character. And finally, we do a train test split. Think of it like this. We hold back some of the data for later. That's for the final exam, to make sure our model works on stuff it's never seen before.
Okay, our data is sparkling clean. Now for the really fun part: model development. This is where we take our pristine set of clues and use them to actually build and train the brain of our digital guardian.
At the heart of this whole thing is a machine learning algorithm. Now, that sounds complicated, I know, but don't let the term scare you. Just think of it as a set of instructions or rules that we give to a computer. Its job is to study thousands, maybe millions of past transactions and learn the super subtle patterns that separate a normal purchase from a fraudulent one. Now, there's not just one way to teach this thing. We've got options, different coaching playbooks, you could say. Logistic regression, that's your solid, reliable, straightforward approach. Random forest is a bit more complex. It uses like a whole committee of decision makers to get a verdict. And then you've got beasts like XGBoost, which is a high-performance, championship-level strategy. The one we choose really depends on what we need our system to do.
So once we've picked our playbook, the training begins. But it's not a set it and forget it kind of deal. We need to fine-tune all the settings, and this process is called hyperparameter tuning. Honestly, it's a lot like tuning a guitar. You just keep adjusting the knobs and dials until you find those perfect settings that let the model perform at its absolute best. All right, so we've built the model, we've trained it, it thinks it's pretty smart, but is it really? Phase 3 is the final exam. This is where we grab that test data we set aside earlier and see how well our student actually performs. And that's the big question, right? How do we even know if it's any good? What does good even look like here? Acing this test isn't just about a simple pass or fail. We need a way more detailed report card to really understand its strengths and its weaknesses. So to really grade this thing, we look past simple accuracy. We focus on two really important metrics. Precision is all about this. When our model yells fraud, how often is it actually right? We want this to be high to avoid annoying you with false alarms. Then you've got recall. That's asking, of all the actual fraud out there, how much did we manage to catch? You want this high so threats don't slip through. It's a balancing act, you see, and all of this gets summed up in something called a confusion matrix, which is basically the model's super detailed final report card. Our model passed its exams with flying colors. It's showtime. Now we get to do the most critical step of all, releasing our digital guardian out into the wild to start protecting real accounts. This is model deployment. So going live isn't just flipping a switch.
First, we move the model into what's called a production environment. Then we create an API endpoint. Think of it as the digital front door that lets real-time transactions ask our model for a verdict. And of course, the whole thing has to be built on an infrastructure that can handle millions of transactions a day without even breaking a sweat.
But here's the thing. Our job is never really done. Far from it. Fraudsters don't sleep. They're always changing their tactics. That means we have to monitor the system constantly. We track every prediction. We log everything. We're always on the lookout for something called model drift. It's a fancy way of saying the model's performance is starting to slip because the real world has changed. And if performance drops, we need alerts to fire off immediately so we can jump in and fix it.
All right, we're at the final phase, and this one is so important for making sure our system is reliable and consistent. It's called containerization. This is all about packaging our entire system up so it can run perfectly anywhere, anytime. Anyone who works in tech knows this dreaded phrase, but it worked on my machine. You can have a system that runs flawlessly in the lab, but then it completely fails in the real world because of some tiny difference in settings. Containerization, using tools like Docker, is the cure for that headache. It bundles up our system and everything it needs to run into one single package, a container that runs identically no matter where you put it.
The whole process is kind of like packing a really sophisticated lunchbox. We use a tool called Docker. We write up a recipe, called a Docker file, that lists everything that needs to go inside. Docker then builds this perfect self-contained little package, and boom! With one simple command, we can run our fraud detection system anywhere, and we know it's going to work perfectly every single time.
And there we have it. We're back where we started, looking at the whole blueprint, but now we can see the full picture. We've literally gone from a single tiny data point all the way to a complete end-to-end system. Every single step, from collecting data and training the model to deploying it and packing it up in a container, it all works together to create that powerful digital guardian.
But, building this system isn't the end of the story. The world of fraud is a constant arms race. It's a continuous chess game. As our detection methods get smarter, you can bet the criminals are getting smarter too. So that leaves me with one final thought for you. What do you think is next in this crazy ongoing battle between protection and deception?